Hello everybody, Math Hobo here, and today we are going to be talking about the great Parallel Axis Theorem. So not only will we be discussing it, we will be proving it. We will be deriving the theorem. So let's begin. So the Parallel Axis Theorem says that if you have some rigid body, and you have the moment of inertia of rotation around the center of mass of that rigid body, then if you have a parallel axis, an axis which is parallel to the one which I have drawn here, which is located distance d away from the original axis, then the new moment of inertia about this point, let's call this point P. So the new moment of inertia about this point P is given by IP is equal to ICM plus the mass of this entire rigid body times d squared. So this is the parallel axis theorem. And today we will be deriving this, and it seems out of the blue. It seems to work quite well with our idea, but we don't know why. So we will be using a lot of integral calculus and a lot of center of mass concepts to help us derive this. So let's begin. We have some rigid body, and that's a bad rigid body. That's better. So let's have our center of mass to be here. That's Cm. And we have an axis going through that, center of mass, and let's define some dm. Now, what this dm is it's simply a tiny infinitesimal section of our rigid body, and we'll be observing how it moves. So note that we'll embed this rigid body on a 2D Cartesian coordinate plane centered about the center of mass. So this will be x, and this will be y, and we will be rotating it around the y-axis. So let's observe the motion of this small dm infinitesimal mass here. So if we have some x distance, let's call that rcm x, then what'll happen is our dm will move in circular motion with that radius for its circular motion. And now let's go ahead and define a new axis which it will rotate around, which will be our axis centered about the point P. And note that these two axes are parallel, and they must be parallel for this theorem to work. So we have our new axis, and let's say, actually wait. Wonderful. So then we can, if the new axis going through a point P is parallel to our original axis, which goes through the center of mass of the rigid body, then and if this distance here is defined as d, then we have the relationship between the radius given by dm to p and dm to cm being r of p comma x is equal to, r of p, let's just say, is equal to rcm x plus d. So this is wonderful. Now, what we must realize is that for this theorem to work, we must be given the original moment of inertia about the center of mass. So what we do know is the integral r squared cm times dm, which is equal to ICM. So let's remember this, and actually let's write it smaller so that we have a little bit more room to work with on our blackboard. So ICM is equal to the integral of RCM squared dm. And now let's because we want to observe the moment of inertia about our new axis centered about our point P. So let's go ahead and write out the description for the moment of inertia about the P axis. Then we have IP. Actually, let's write it up here. We have IP is equal to yet another integral, which is integral rp squared dm. And now we have a solid definition for rp, which is rcmx plus d. So let's go ahead and substitute this for into our integral. Then we have ip is given by the integral of this rp squared, and rp squared, let's just write this out really quickly, rp squared is equal to rcmx squared plus 2rcmx d plus d squared. Yes, so this is just the expansion of a plus b whole squared. Wonderful. So then we have ip is equal to the integral of dm into rcmx whole squared, rcmx squared plus 2rcmx d plus d squared. Wonderful. Now we can erase this. And what we have, when we expand this integral and we separate it out by adding, by separating the integral of a sum into a sum of integrals, we have ip is equal to integral rcm squared dm plus 2d rcm 2d integral rcmx dm, and then plus integral d squared dm. So we've just expanded our integral, which is, as we remember, ip. So it's the moment of inertia about p. And let's go ahead and evaluate this. Well, this term looks very familiar, and that's because it is simply the moment of inertia about our center of mass. We have defined that earlier here. So integral r squared cm dm is simply ICM. So let's rewrite that as ICM. So ICM plus, and then we have this 2d integral RCM comma x dm. And we'll get back to this term, but let's go ahead and evaluate this term first. So plus integral d squared dm. Wonderful. So integral d squared dm is simply equal to 1/3 d cubed. Oh, no. My apologies. Integral, so we factor out the d squared, and d squared integral dm is simply equal to d squared m. So then this term becomes md squared, and we have ICM plus md squared plus 2d integral RCM x dm is equal to IP. And now we have, we're achieving something that's vaguely familiar to our previously stated parallel axis theorem. It's just that we don't have this term over here. So what we would like to do is prove that this term is equal to 0. So to do that, we must realize the significance of the center of mass. So let's ask ourselves what the center of mass actually means in terms of x components and y components. So remember that we defined our axes, x and y, and we embedded it, and we embedded our rigid body inside a coordinate space, and we centered the coordinate space around the center of mass. So that means that the sum, if we split the rigid body into two separate parts, into two halves, which is cut down this y-axis here, then we have the sum of dm I. So the sum of dm I, so the ith dm, it multiplied by RCMX, which is simply the radius from the y-axis. So each infinitesimal mass element multiplied by its respective radius from the y-axis will be equal to 0. And let's ask ourselves why this is. Well, that's because over here all the radii will be positive, so we'll have basically the integral of RCM dm, and over here all the r values will be negative, so we'll have minus integral RCM dm. And if you think about the rigid body that we have here, and if we take a pencil and we balance it on Cm, then both of these sides' weights should cancel out. And what that basically means in concept of torque is that the left-hand side sum of dmi times RCMX plus the right-hand side sum of dmi times RCMX will be equal to 0. So now that we have this, we can simply rewrite it as an integral, and we have integral dm RCM x is equal to 0. Wonderful. And well, what is this term? This term is the same thing as this term. So we realize that this is simply equal to plus 2d multiplied by 0. And well, what is 2d multiplied by 0? That's simply 0. And we have plus 0. And well, we can just get rid of that. And then we are left with our parallel axis theorem, which states that IP is equal to ICM plus MD squared. And this concludes our section on the parallel axis theorem. Thank you very much.